Hello. So I'm just doing a quick sound check. It all looks okay. My camera not working for some reason. I think it is. Okay. I'll just while I'm getting that set up there, guys. My name is Shane Murphy. I'm technical and sales director at Ashgrove. Thank you very much for joining us. We will be normally with this presentation somewhere around maybe 45 minutes. If anybody wants to contact us afterwards, please feel free. The purpose of this presentation, I suppose, over the last probably year and a half, I guess, since electricity prices have jumped significantly, they've more or less doubled, I suppose. Now they're on the way down again slowly. But we're, I suppose, getting some horror stories, or we're hearing from people that they've heard stories, and there's probably maybe 10% of them that are true, and some of them aren't. And it comes down really to like anything, understanding the piece of technology and making sure that it's being installed and set up correctly. And we're going to talk a little bit about it. This isn't going to be a technical talk. There will be a little bit of it mildly technical, unless people have really technical questions. I'll answer them maybe simply, or we'll take it offline. We can answer them afterwards. And we'll go through some calculations of maybe what a good installation would look like, and then in the very same house, what a poor installation would look like. And what I mean by that is taking the same heat pump, whether it's a tier 1 heat pump, which is what you need in Ireland, kind of a decent quality heat pump. If we install that heat pump badly, what it looks like. If we install it well, what it looks like. And you can see that the difference in operating costs can be 3 to 4 times higher when it's badly installed, and where our installer doesn't understand maybe the implications of some of the decisions. Now, some of this is down to maybe architects, engineers, homeowners' decisions as well, where they don't maybe fully understand that maybe while like floor coverings or certain things which do affect heat output, they can have a detrimental effect on 1 room out of 10, let's say. But unfortunately, if you do have a scenario, we'll go through it. But it's, heat pumps are a technical piece of kit. They're not as forgiving maybe as an oil or a gas boiler. They're extremely efficient if used correctly. And what we're doing today is, I suppose, to arm you with information so that, number one, you're not afraid of heat pumps. There's a reason why they're being pushed all over the world today, right across Europe. But if you put it in the hands of somebody who's not into understanding or taking the time to read manuals or any of that, unfortunately, you're going to end up with running costs which are twice as high, maybe 3 times as high, in really serious cases up to 4 times higher than they should be. And so we'll be going through that, and so we'll talk about what you do, what you ideally shouldn't do, and then the tips and tricks and so on. So you have a little questions tab on the bottom of your screen there. I'll be keeping an eye on it here. So if you type in any questions, I will keep an eye on that and answer as I'll either answer as I go, or I'll answer it at the end if the question isn't relevant at a particular point. So here we go. So we'll cover the heat pump technology, a little bit about how it works. We won't go into the vapor compression cycle or any of that. We'll talk a little bit about why it doesn't work sometimes. We look at the running costs. We compare good and bad, like I said. We look at air source versus ground source. We seem to be getting quite a few inquiries these days for ground source. And I'll give you my honest opinion again. We look at the maths. What does the maths tell us? Should I go air source or ground source? We talk about the size of them and where they would sit inside in your house or outside your house. And then we'll talk a little bit about controls and the myth versus reality. We hear a lot about heat pumps that you have to leave it on, don't ever again touch it. Some of that is laziness. Some of it is people don't have the information, so therefore don't have it to tell the homeowner. But in some houses, probably 20 or 30% of houses, they should probably be controlled in a way that is closer to an oil boiler, in that you might control it in more of an on-off fashion. Certain houses you should not do that, but it's not a one-size-fits-all. And we're going to hear, I suppose, one-size-fits-all here a lot, unfortunately. And you know, the same rule gets applied across the board, and it simply doesn't work. Tiny bit about Ashgrove, won't bore you. We're in business since 2001. We've been doing heat pumps since then, since 2001, underfloor heating also. We have about 18,000 systems in operation around Ireland and the UK. We have systems installed from 2 kilowatts, so that would be something like a small apartment, 2 kilowatts up to 2,000 kilowatts, which would be, you know, a huge hotel, or maybe a large factory, which is, you know, maybe food processing or an abattoir or something like that. Last year we did about 1,700 projects, all including heat pumps. We're doing this series of webinars for homeowners and professionals. It's free advice. You know, we're not going to be pestering you guys with emails. These are, you know, we're doing over about, I think it's 200 webinars this year. They're all free, and I can guarantee you we won't be chasing it. We can't stay in contact with the people we should. This really is free information to help professionals and homeowners make informed decisions that maybe otherwise you're reliant on, you know, somebody who maybe isn't fully up to speed, but you might end up getting poor advice. So we have a lot of how-to videos available on our YouTube channel. We're working that all the time, and so on. So look, we're by the way, Ashgrove is a registered one-stop shop, which means that that's from a home upgrade perspective. We won't really be talking about home upgrades here. We'll be talking about heat pumps, so it could be new build or it could be a retrofit or older houses, doesn't matter. Again, we're part of this Irish Solar Energy Association, and we're a Board GOT premier solar contractor. So anyway, just a little bit about us. So if you look at our website, you'll see 4 things. You'll see solar energy, home energy upgrades, new homes, and you'll see agri and business. That's typically mainly solar these days with agri. But from a home upgrade point of view and a new homes type project, obviously heat pump is central to all of it. So I'll just give you some maybe quick examples of projects. These are projects we've done, all of these big ones. Well, yeah, all of these 3 that I'm showing you are all in the UK. Big project in Reading, air-to-air heat pumps. The next one is a project in Scotland. It's a containerized 1.2 megawatt heat pump pod. They're built in Ireland. We design them, build them, the whole lot. And the last one is again in Scotland. Again, that's a 2 megawatt lake source heat pump. We build everything there, you know, the electrics, the pipe work. We design it, we install it, we build the controllers for it. The reason we show projects like this is for anybody coming on to these talks to hear about heat pumps. Well, obviously, you need to know that the people you're listening to have a history of heat pumps. And when you go up to this size here, you know, it really separates the men from the boys. You know, anybody can put in a 5 kilowatt heat pump. The question is, if it's not working right, you know, do they have the capability and the understanding to fix it? You know, so hopefully that gives you a bit of confidence of our history. So before we, I suppose, go launching into it, why are we being pushed down the road of heat pumps? Some of you will already understand this, but at a high level, they're cheaper to run. They're 70 to 80% less carbon than oil or gas, right? Of course, that will be cleaner over time because more and more of our electricity is now coming from wind and hydro and maybe some batteries and so on. So there'll be less and less fossil fuels involved. So today it's 70 to 80% cleaner. In places like Norway and Sweden, it's more than 95% cleaner because they have so much hydro. Places like France, they have more nuclear, but again, there's no carbon associated with it. I know it has its own limitations, but there's no carbon. So these countries are, you know, further along than we are. But we're getting there fast. Our electricity is 50% cleaner than it was only 7 or 8 years ago. And over time, that'll get better and better, which means that your heat pump, if you install it today, will be, I'm just going to say, 75% cleaner than oil. Well, in 2 years' time, it'll be 80% cleaner than oil, and so on, due to electricity getting cleaner. Of course, over time, Ireland should gain energy independence if we start putting up the wind across the western seaboard, maybe that we should have. We know that our wind along the west coast is equivalent to in value to the GDP of the country. So a very valuable resource, but would allow us to not care about what happens in places like Russia or these places, at least from an energy point of view. So okay, so the big thing we're hearing about here all the time is about cheaper to run. I've just thrown it out there as if it's a fact. I'll be proving that to you as you go, but we go through the maths. But why are we hearing these negative stories? You're all hearing them. I'm hearing them. We've been hearing them for probably 17 or 18 years now. You know, there are poor heat pumps in the market. I would say not a lot, but we are very price driven in the Irish market. And because we don't have the same experience we might with, say, cars, we know that some cars are efficient, we know some cars are not. And if you pay more for a car, there's a likelihood that you get a more efficient car. That's not, of course, always true, but at least your average person looking at an average car, you know, there's a general awareness. That does not exist, of course, with heat pumps. So if I see a Rolls-Royce heat pump and a cheap heat pump beside it, sure, how does your average person know the difference? And so, you know, without knowing the difference, they typically go for the cheapest. And of course, in some cases, that's fine. In some cases, it just doesn't work. The big culprit really here is badly designed and installed. So we look at, I suppose, the what bad looks like, and as a consequence, I suppose, well, what does good look like, and how can we achieve that and make sure? By the way, this isn't a case of putting a heat pump in and hope that you end up in the good scenario. This isn't a, maybe, how would you say, a kind of a 50-50 lottery. If you design it well, your outcome is guaranteed, right? So sadly, that's not what we see in the industry. I would say probably 80% of what we see out there is quite poor, if not extremely poor. Some people are just seeing that their electricity costs have gone up. They might have gone up from €1,000 a year to €1,800 a year, but they forgot maybe that their oil, which was £2,000 last year, has now disappeared. So sometimes it's that. And then I think I'll skip that one. The other thing people often do is, you have to be careful of this, when you put in your heat pump, because they think that it's cheaper energy, they tend to be a small bit more flahool with the temperature. So, you know, it gets bumped up to 22 degrees where previously it was 20. Well, you know, every degree that you bump up the temperature, it's going to cost you about 4% in your bill. So just be careful with that. Okay, so before we launch into the maths, just a general understanding of how a heat pump works. We all know a fridge or a freezer. We know that they do work. We don't know how they work, but I'll just, I suppose, explain that inside here, you will feel, if you put your hand on the back of the fridge, you will feel a cold surface. That cold surface, because it's colder than everything around it, starts absorbing heat. Okay, we won't go into any more than that. It passes through the seal expansion valve and the compressor, and you end up getting the heat rejected at a much higher temperature at the back of the fridge or freezer. So that's the end of that. We know it works. The reason that we like it is that it's an extremely efficient process. Okay, it runs on electricity, which, as we say, is more and more green, let's say. And so let's look at a small bit on the numbers. So if I take a typical heat pump here, this is a Thermia heat pump that we bring in from Sweden. If we put in a kilowatt into the left-hand side, the heat, we're using that to collect about 4 from, in this case, it could be air or it could be a ground source heat pump. So you're paying for 1, you're harnessing 4, and what comes out the right-hand side here is 5. So you might have heard about this efficiency term, COP. It's called coefficient of operating performance. Don't worry about it. All it is it's the relationship between that 1 that you paid for and this 5 that you get out. So obviously, if I'm paying for 1, I'd like to get 5 out, 6 out, or 7 out. I don't want to pay for 1 and get 1 out. So the heat pump is giving us a ratcheting or a multiplying effect. We want that to be as high as possible, right? For this reason, if I'm paying 30 cents for day rate electricity, and if I'm getting 5 out, having paid 30 cents, well, that's costing me 6 cents per kilowatt hour by the time it comes out. We know that oil is up around 12 or 13 or 14 cents, whatever it is. So if this number gets smaller, right, obviously my cost here goes up. Okay, so I want the most of these out as I can. Now, there's 2 or 3 things that are involved in that. Number one, obviously, the heat pump has to be high quality or decent quality. And the rest of it then is really down to design and installation. We'll be talking a little bit about that. The other thing that 1% of you might be interested in, I suppose, is the electricity going in here today is 250 grams roughly of carbon per kilowatt hour. And when I divide that by 5, coming out the far side, it's at 50 grams. Okay, so our electricity 7 or 8 years ago is around 500 grams of carbon per kilowatt hour. Somebody like Norway is 13 grams, right? And if I divide that by 5, of course, I'm down at whatever it is, about 3 grams. So practically zero carbon heating. So we have a long way to go before we get to 13, but we've come from 500 less than 10 years ago. Again, France is 67, Sweden is 17, and so on. Some place like Poland, then, which is still reliant on coal and so on, might be up still at 450 or 500, maybe 600 at times. So, but all of Europe is evolving, and we know it's all going to green electricity ultimately, or as much as is practical. So that's a tiny bit about the math. So we're worried about that that figure, the 1 to 5 ratio. We'll be calling it COP, coefficient of operating performance, right? And I'm just going to click on that button just to show you the cost. You'll find this yourself with SEIs. Of course, anything, I'm on the wrong screen now, you can't see this, but if you go on to SEIs, and I'm minus my trusted sidekick today to help me with the technical side, but if you go on to SEI's energy cost calculator or comparisons, it tells you the cost of oil and gas today versus heat pumps. And you know, they don't have, I suppose, skin in the game, maybe the same as we do, but it'll give you the you can compare side by side, but of course they're comparing a good heat pump with a good boiler, and they're not taking into account maybe the you know, heat pumps sorry, boilers are easy to understand. We've been at them now for decades. With heat pumps, they're more sensitive to guys and poor understanding, etc. So I'm just going to launch on here and just show a heat pump at 35 degrees. Right, so that's the water leaving the heat pump going to your underfloor heating or to your radiator. So at 35 degrees, that figure that we showed a while ago, the 1 to 5 ratio, the COP here is 4.5. If I increase the temperature to 45 degrees leaving to go to underfloor heating, it's now dropped to 3.49. Keep in mind, we want this figure to be as high as possible because it reduces our running costs. And if I run it at 55 degrees, I'm gone to 2.81. So, you know, I've reduced my efficiency there by, I'm going to say, firing from the hip, somewhere around 40%. So that means I've more or less doubled my running cost by increasing the temperature coming out of my heat pump. So 35 degrees is underfloor temperature. 45 might be a low temperature radiator. 55 would be the absolute highest that we would ever design with a radiator system. We would typically design maybe down here or lower, and that would really only be on the coldest day of the year. But what I'm trying to say here is that by controlling the temperature coming off the heat pump, you can affect your efficiency. Now, we compare this to driving your car. It's very efficient at 50 miles an hour or whatever that is, 80 kilometers an hour. But if I drive it at 100 miles an hour, it can certainly do it. But we all know, you know, that it really, really affects your efficiency or your fuel economy. That is not understood in the heat pump industry. And when we have a situation like that where the system is designed to run at 55 degrees, where it could have ran at 35 degrees, you know, and my running costs are now twice as high. Of course, by nature now, we blame the thing that we don't understand, which is the heat pump, instead of blaming, you know, are the pipes too small? Is the pump too small? Have I the wrong floor coverings? Are the radiators too small? Have I got covers over the radiators? A whole series of things that we don't have the experience yet in Ireland to understand. So that's the big thing. Any of you there, eagle-eyed, will see that I've chosen here 7 degrees. That's the outdoor air temperature. So heat pumps in Ireland will operate down to about -20. we use Mitsubishi, we use Daikin, we use a German one called Alpha Innotec. They will all operate below -20. Now, what you'll see is that as the air temperature goes down, so does the efficiency slightly. But people get very emotional over that. And something happening here. Okay. I get very emotional over that because they think that, you know, at -5 or whatever it is the be all and end all. Less than 1% of our time over the heating year is down at really low temperatures, you know, maybe below my, down at -4, -5. And so we take a slightly different view of these COP figures, and we use what's known as a SCOP, a seasonal coefficient of performance. And what that does, it takes the good with the bad, because, you know, obviously if I have 13 or 14 degrees outside, my efficiency of my heat pump is going to be maybe 7 to 1. In the really cold weather, if it's -7, as you can see here, it's going to be, what did I say? Sorry, apologies. It's going to be, in this case, whatever it is, 2.5 to 1, right? So we don't want 2.5 to 1. We certainly don't, right? We want 6 to 1, 7 to 1. But we take a seasonal look at it and we're realistic with it. But we're not throwing things in and hoping for the best. So it's quite scientific. Okay, so I'm just going to skip on from there. So just to show then, why would I use 55 degrees where I could use 35 degrees? We see some houses are operating at 26, 27 degrees and still being able to heat. Obviously, I have an efficiency now of about 7 to 1 or 700% efficiency if you wanted to look at it like that. So I just wanted to make the point, anytime I'm talking to, or we're talking to a homeowner, they think that their windows are, you know, they might be, whatever you want to call it, AAA rated, or, you know, super duper, or passive insulation, passive standard, or whatever it is. But your typical window today, you know, that we see in an old house, it might be, there might be 2.5, they might be 3, but kind of, you know, an average new build, it can't be probably worse than 1.4, right? It might be 1.2, it might be 1, but your average wall is 0.27, or it might be 2, or it might be 0.17. So your average wall is 6 to 10 times better than your average window. Okay, that's a very important thing to know. People think because they spent 40 grand or 70 grand on their windows that, you know, Shane is telling me my windows are rubbish. They're not. They're just not insulation. So, and so a lot of windows equates to a lot of heat loss. People get fixated on the fact that at certain times of the year it will overheat, and there, you know, we can blame the windows for that. If you have a lot of glazing facing the sun, it'll take heat in, but that's typically June, July, August. And so it overheating on those days is no good to you in December or January when the sun goes down, because the heat will only be going one way, and that's out. And so I'm going to, 2 seconds, I have some questions there coming in, guys. I'll see what they're just wondering. Yeah, okay. Okay. So I'll come back to it in 2 seconds. There's 2 questions sitting there. I'll come back to them in 2 seconds. So I just want to make the distinction here between these 2 houses. So the house on the left, you know, we can derive maybe that those are very expensive windows, but I can tell you that when the sun goes down, the heat is leaving through those walls, as I say, 6, 7, 8 times faster than it will through a wall. And so therefore, without doing any calculation, I can tell you that the room on the left there is going to use probably somewhere maybe 80, 100, 120, 150 watts per square meter for that room. I can tell you that the house on the right, the heat loss is going to be maybe 30 watts. It might be 40. There isn't a lot of glass here. So it's going to be losing 3-4 times less heat overall. Okay, what does that mean? It means different things. So we'll come back to it in a second, but just to appreciate that there are different types of houses. And you could actually have a room that is, 1 second. 2 seconds, guys, sorry. So you could have a room like this with a lot of glass, which is attached to a house like this, which kind of, on average, doesn't have a lot of glass. And therefore, that room might be using, as I will show you now in an example, that room can be using 8 or 9 times more heat per square meter than the rest of the house. And that creates a big problem, right? The approach for this, if you go into the typical shop, throw in plenty pipe and so on, but you need I suppose a trained person looking at this. So the house on the left here will certainly be using a significantly more, will use more energy over the year, and on the given day, instantaneously, it will need a lot more power. So that makes the heat pump bigger, it makes the running costs higher, etc. So, right, I'm going to go on here. So here's an example. This is a project we did in 2009. The house on average, other than this sunroom, so this sunroom is a little bit like what we just looked at. It has these are double doors, but this glass goes all the way up to the apex, so it's kind of V-shaped at the top. There's 3 outside walls on it. My button isn't working here for some reason, guys. Jesus, the worse it's getting. Okay, I'll go back. Sorry. Apologies. So we'll start there. So this room, that you can see my mouse there, is using, in this case, we can see here 13 watts is what the house is using on average. That room is using 109 watts. We've been measuring it now for quite a while. So I haven't done the calculation, but it looks like it's probably 8 times more heat. But of course, the floor isn't any bigger. And so the question is, can I get enough heat out of that room to deliver, let's call it whatever it is, 1.1 or 1.2 kilowatts, right? And so in terms of heat loss, the room is this size, but in terms of in actual fact, the floor is only that size. So we look a tiny bit on how we do the calculation for this. We calculated that the room is going to need 109 watts. If we look at, don't get too afraid of this chart now, I'll only be looking at a few parts of it. We look at 30 degrees, which we looked at a while ago, and we asked the question, can I heat the house through, in this case, it's a tile floor, right? So tile floor, so in other words, zero resistance to heat transfer. You can imagine, you know, something like copper or something like that. If I heat one side of it, that the heat will pass quite easily through it. Insulation will not, timber less so, carpet obviously much less so. It's, like a duvet, it'll keep heat in. So my question is, can I heat, first of all, the rest of the house here, right? 13 watts. Well, at 20 centimeter spacing, so people will put in the pipes at 8-inch centers, and at 20 centimeters and 30-degree water going into the floor, I can get 49 watts out, and I only wanted 13. So that's more than I wanted. In fact, I'm going to actually start overheating now if I do this. So I actually need to drop that temperature down below 30 degrees. It's not shown on the chart there because we don't worry about it if it's below that. We're worried about being underheating. It's always easy to turn it down. In some cases, you can't turn it up. So we know we can heat the rest of the house. The question is, can we heat the conservatory at 109 watts? Well, at 20 degrees, it's if I go to 35 degrees, like we just said, I'm getting 75 watts. At 40 degrees, I'm going to 99 or 100 watts per square meter. And if I go to 45 degrees, I'm getting to 124. So I'm more than heating the room now. The problem now is, yes, I can heat it. I can see here that my floor surface temperature now is getting quite hot. I'm not going to get too bogged down in that today, but if I can feel the heat of the floor through my shoes, there's something wrong with the system. We would expect to see a temperature, anything you see in the salmon color here, to us, you're inside in a car showroom or something like that, where there's a huge amount of glass, and we need to get a lot of heat out. But that's not a comfortable place to be now if the floor is shoving on for showering temperature, right? So yes, we can heat that conservatory with tile, but it's at 45 degrees. Now, however, if we put the pipes in, not at 8-inch centers, so 8-inch apart, if we go to 6 inches apart or 4 inches apart, we'll just look at what that looks like. So 4 inches or 100 millimeters. So now I can actually, at 35 degrees, I'm at 100 watts, and at 40 degrees, I'm at 133 watts. So we're probably operating now at, on the coldest day of the year, we're operating at 36, maybe 37 degrees going into the floor. Okay, so now we can do it. So, it's not desperate for our heat pump at 35 degrees. We know the efficiency is 4 or 5 to 1. So that's quite interesting, but we did have to go to 4-inch centers to do it. If we put it in like every plumber in the country at 6-inch centers, we'd have had to go more or less to 40 degrees, slight impact on efficiency, but not drastic, I'd have to say. But if we had put it in like we used in the olden days at 8-inch centers, you're actually up here now at 45. So by putting the pipes in at the wrong centers, we've increased the running cost. But importantly, we can heat the room. Okay, so now I'm going to jump on to another chart. I'll come back. So that answers one of the questions there. How do you find out the water temperature? The water temperature is dictated by how much loss there will be from the room. We calculate that from U values. And if we get, let's say in this case, 74 watts or 74.9 watts, and we have the pipes in at 20 centimeters, we know that we have to run that heat pump at 35 degrees. But being honest, we would know that long before, and we would actually tell the homeowner or the plumber or the architect we need to put the pipes in at 6-inch centers or 4-inch centers or whatever it is, because we're worried. It's typically only one room in the house here that we're worried about. Unfortunately, if we have one room which is not designed properly, it drags down the efficiency for the whole house. I'll come back to your question in a second, Brian. So anyway, I'm happy to make available any of these slides I have here for you. But the question we're asked all the time is, can I use carpet or timber? And I've just taken a few excerpts there from timber and carpet websites. What you can see here is, you know, the typical carpet is 1 to 2 tog, but you should always check with the manufacturer the suitability for underfloor heating. Now, they will always tell you it's okay. I've yet to come across somebody who understands. But if I put down a thick carpet in the room we just looked at, and what they're saying in this case is it should never exceed 2.5. So that's like tog now, like you'd have in a duvet. You can imagine putting a duvet there now down on the floor we just looked at. Any one of us would know intuitively that it has to have a negative effect. If I put a duvet up on a radiator and I was wondering why the room wasn't hot, you know, anybody who walks in would be able to say, look, you clown, would you at least take the duvet off the radiator? You know, we need know nothing about heating to understand that. The same understanding is not there for underfloor, right? The guy in the shop told me the carpet is suitable or that the timber is suitable. All he's telling you is that it won't go on fire. He has no idea of the amount of heat that's required for your room or how much the carpet or the timber will allow through. Here's an excerpt from a different website. The great news is you can definitely put carpet on underfloor heating. In fact, it's a very suitable choice. Blah, blah, blah. Okay. And then again, the tog value should not exceed 2.5. I'm going to show you from our charts here what that means. And I'm only going to 0.15. So a tog, when we convert it into resistivity, we divide by 10. And that's so a tog of 1.5 is 0.15 here. But just to show you, so to recap, the room we looked at a while ago was 109 watts. With a carpet, what they're saying to us is there's no problem, right? We can go up to 2.5, which would be 0.25 here. But here's what it'll do. So if I put my pipes in at 20 centimeter spacings like we would, even at 50 degrees, I can't heat the room. Right, so I've destroyed the efficiency of my heat pump and I still can't heat the room. If I put the pipes in at 6-inch centers, which would be viewed in Ireland as the, look, just throw it in at 6-inch centers, it'll be safe, which would be I would say 99% of the industry would do. We still can't heat the room with pipes at 6-inch centers. And even with pipes shoved in at 4-inch centers, you can't get them in any tighter than that. We still can't heat the room and we have halved the efficiency of our heat pump. In other words, we've doubled the running cost. So now, what's after happening here? We're after relying on a guy inside in a flooring shop to design our heating system for us, even though he has no idea of watts per square meter, heat flux, or any of those floor surface temperatures that we're looking at. So unfortunately, because they'll hand you a bit of a cert and all the rest of it, that basically says this product is suitable for underfloor heating. Any more than that, none of them will ever ask how many watts do you need per square meter out of this flooring. In 20 something years, I've never heard it, you know, so, and that creates a huge problem. Okay. So let's only go through that again. So here's what an example of a good, I'll come back to your question, Brian, and keep an eye on it there. So I'm answering the other ones as we go. So here's an example of a running cost, which is average glazing, high air tightness. So the house is 220 square meters. We'll just take that as kind of a, I don't know whether it's average or not. Maybe for a one-off house, it might be average. Average glazing, so call it, average amount of glazing and average U value. But it's highly airtight. It's been built recently. It's a tile floor, right? Or at least in the critical rooms. We can see in the other rooms in the house we just looked at where I need 13 watts. Well, I can actually put carpet down in those rooms because I'm going to get 13 watts through the carpet. I can get 13 watts through timber. It doesn't matter. But if I put carpet or timber in that critical room that we just looked at, I won't get 109. And I drag down my efficiency for the whole house. There's actually a worse impact than that. I'll go back to it in a second. If I'm using radiators, that the radiators are the correct size. We've designed the radiators to put out enough heat at 35 or at 40 degrees. If the radiators are too small, obviously, we can all envisage that they now have to be hotter. So the heat pump has to be running harder and it drags down the efficiency. So sometimes I would say this is extremely rare that the cylinder is wrong, but you can have a cylinder and somebody takes out the boiler, puts in a heat pump. The cylinder is the same one they always had. The coil inside and that transfers heat. You can imagine if that's too small, it's the same thing as having a radiator that's too small. So again, it increases the running costs. And we're assuming that the house is set to 21 degrees. Okay, so I'm just going to run through the calculation. We won't get bogged down, but we know that an average house being built today, or a house that's being retrofitted, an old kind of 25 or 30-year-old house that's being upgraded, will get to somewhere around 26, 28 kilowatt hours per square meter. That's the amount of energy the house will use over a year. So the house is 220 square meters. We multiply it out, that gives us 5,700 kilowatt hours for heating. We add hot water to it. We're going to add 3,400 kilowatt hours, being a standard amount. We know for an average family of 4, it's somewhere around there. Some will be higher, some will be lower. But when we add them together, we get 9,120. Now, if it's up or down a bit from there, look, we could be wrong sometimes by 5 or maybe up to 10%, depending on how people use the house, how much hot water they use. But we won't be out by a lot. Then I've taken an average efficiency of a heat pump here at 400%. So I'm going to divide the 9120 by 4 because of that 1:4 ratio. And I'm going to get our running cost here. And in this case, I've taken electricity at 30 cents. Keep in mind, a year ago or a little bit more, it was 40 or 42 cents. So the running cost here is 684 euro. Now, but keep in mind, everything over here is working in our favor. I don't have an awful lot of glass. The house is airtight. I have a tile floor in at least the critical rooms, or the radiators are the correct size, or they're not covered. I wouldn't worry so much about the hot water cylinder, but it doesn't. We never see it causing a problem, but it can. And then we have an average temperature in the house. That it's not every now and then we see somebody come in from the Philippines and they want 27 degrees. That's fine. We can do it, but the heat pump has to get bigger, and of course, the running cost goes up. Anyway, I shouldn't be picking on the people from the Philippines, but we have seen it literally. So I'm going to compare that now to exactly the same size house, 220 square meters, but lots of glass, right? Keep in mind, all I ever hear when I hear about the glass is, oh, Jesus, Shane, I don't know how we're going to keep it cool, right? And that might be fine in June, July, August, or maybe even sometimes in January when the sun is low in the sky, you get some solar gain. But in general, over the year, lots of glass means lots of heat loss. And overheating in summer is no use to you when you're underheating in winter. It averaging out is no use to you. As the guy says, having your head in the oven and your feet in the fridge, on average, I'm okay. Well, that's no use, So poor air tightness, underfloor heating with the wrong floor covering, right? Or undersized radiators. Now, when I say wrong floor covering, it could be the wrong pipe centers as well. We put the pipes in at the wrong centers for some reason we didn't understand, or we didn't calculate, or we didn't do anything. Or we put, when we're finished the house, somebody decides, I'd love these radiator covers. They're going to add 30% to your running costs. Bad hot water cylinder, and I'm still saying 21 degrees here, but if it was 22 or 23, obviously it impacts the heating costs. So what does it look like? So now our heating load is gone from 26 to 50. straight away, right? My house is still 220 square meters. So now I need 11,000 kilowatt hours for heating. I'm still going to use my same 3,400 for hot water. It could be higher, but we leave it there. So now my total energy usage for the house is 14,400. Of course, I divide that by my efficiency. In this case, I'm just going to say, because I've had to run the house now at 45 or 50, my efficiency of my heat pump drops. By the way, 300 is still good. By the way, we often see it much worse than that. But my running cost now is very simply, no, sorry, I've put in here, somebody has not changed their electricity provider, right, at 40 cent. And we're now looking at the exact same size house with 3 times the running costs. Okay, now it could be worse than that, by the way, it could still be worse than that. Like 50 watts per square, or 50 kilowatt hours per square meter here, you know, sometimes we see that up at, you know, 100, or if it's a really old house, it could be 200 or 300 kilowatt hours per square meter. But we've just taken an average house here, just happened to have a lot of glass, and attention to detail along the way was less than ideal. But now we're talking about 2 grand a year. So we're gone from, what did I say, 680 or something? So 680 to 1920 or whatever the figure is. So the very same heat pump. You can take a Daikin or a Mitsubishi or a Thermia or a NIBA, kind of high-end tier 1 heat pumps, and it doesn't matter. There's a whole sequence of poor decisions here that led to a trebling of running cost. Okay, so that's one of the main things. We have control over everything here, right? Don't cover the radiators. Make sure your floor coverings in those critical rooms are correct. Make sure the pipe centers are correct. As a homeowner or an architect or a BER assessor, that might be harder for you because you don't know, and who do you talk to? Most people will go into the local heat, I was going to say heat merchants, but your normal building supplier locally. The guy there doesn't understand, with respect to him, he probably doesn't understand those charts we just looked at. And so pipe sizing, of course, comes into it. Pump sizing comes into it. If all of those things are wrong, you're pushing on towards a doubling or a tripling, in extreme cases, a quadrupling of your operating costs. So the next thing we come to, I'll answer your question there, Brian. So just wondering how an 8 kilowatt heat pump can have an output over 8 kilowatts. It's a rated output, Brian. I don't know what slide you're referring to there, but if there's an 8 kilowatt heat pump and if it's putting out 9, you know, that's just the way they're rated, if that's what you're asking me. It's rated on its output. If it's putting out 8, it would have been taking in 2 or 1.8, sometimes 2.2. So it's rated on its output, but when they put a name on it, you know, it mightn't be the exact output, but it should be close to it. It might be 8.2, or in some cases, we have some heat pumps there that are rated at 7 and the output is actually 8.2. But it's, yeah, it's not for skullduggery. That's all there. We have to put all of that data up on a database that's right across Europe, and it's all signed off. So there's no, I can't remember if it was on the slide there or why you're asking the question. So I'm going to skip on. So air source versus ground source. So now that I suppose we are hearing about these air source heat pumps being expensive to run, right? I'm after answering the question there, hopefully, for you. In some cases, ground source might be the right choice, right? So we're asked the question all the time, why would I go air source versus ground source? Well, let's look at the calculations and see what it tells us, right? So ground source tend to be slightly more efficient and they tend to last longer, right? Especially if your air source heat pump is maybe by the sea, where you're getting the effect of salty air, maybe blowing in off the sea. All of our heat pumps are treated with a bluefin coating to protect it from salty air. But anybody living near the sea will know it eventually gets in everywhere. We've seen it, you know, inside and double glazing in between panes, and, you know, it gets everywhere. So, so ground source versus air source, here's the argument. Again, we'll take the house as 200 square meters. We're saying 30 kilowatt hours per square meter per annum. So this would be a slightly inefficient new house. Maybe a lot of glass or something like that. We know there's the heating. We'll add the hot water again at somewhere around 3,400. An apartment might be something like 1,700, by the way. A house using a lot of water, a standalone house might be 5,000. It might be 7,000 every now and then. We see a house like, I don't know, JP McManus or something like that, that might be 30,000 or 70,000. You see the very strange ones, but we're talking about average houses today. So we add those together conveniently after getting 10,000 kilowatt hours. If I divide that by typical air source efficiency, that's an average efficiency over the year. So there'll be times when I have 700%, there'll be times when I have 250 or 270%. On average, we'd be expecting to get 400. Okay, so if I divide that, I'm buying from the electricity grid 2,500 kilowatt hours at 40 cent, that's €1,000. Now, if that was 30 cent, obviously that's going to be whatever it is, €750, right? So I don't know whether I deliberately left that at 40 or not, but look, you know, electricity is coming down, so that figure is coming down. Ground source, instead of being 400% efficient, it probably would be 500% efficient, might be slightly more, but on average, it'll be somewhere around there, right? And so carry out the same calculation, divide the 10,000 by the efficiency of 5. It means that I have to buy 2,000 from the grid in order to get the 10,000 into my house, and using the same 40 cent, it's costing me €800 per annum to heat my house and produce hot water. So there isn't a phenomenal a difference in efficiency between air source and ground source. Now, where that €200 becomes meaningful, I suppose, is like the difference in cost is probably somewhere around 3 grand. So I'm spending 3 extra thousand and I'm saving 200 a year. So what's that? 15-year payback, if I'm not mistaken. Where I can say that? Yeah. So but some people just don't want the air source unit out the back of their house, or so that, you know, they might be happy to pay the 3 extra thousand. Now, the other thing is, I suppose, statistically, an air source heat pump is lasting probably around 20 years, where a ground source heat pump is probably lasting 25 years. There probably would be considered, especially the good ground source heat pumps would be considered truly bulletproof. There's slightly fewer moving parts involved, and so they're lasting 25, where an air source will be lasting 20. So you could factor those into your equation. As I said here, the ground source will last about 5 years longer. So then we're down to, what does it look like? Brian, you might confirm that I've answered your question for you there. I hope that's okay. Okay, and the rest is dealt with, I think. So what does an air source heat pump look like? So this would be one that's been retrofitted to an existing house. To give you an idea of scale, it's about 1 meter across here, right? So the top of this would be in around 1 meter, 1.4 meters high. So what's 1.4? That's kind of 4.5 foot high. Excuse me. You can judge it off the door there. I suppose that's kind of the general, you know, if that was a 16 kilowatt heat pump now for a slightly bigger house or a house with more glazing, it might be a slightly bigger heat pump. So it might be, you know, the ones of a foot higher, maybe a little bit wider, but typically that's kind of size. A 5 kilowatt would be, you know, just over half the height of this here. So, but they kind of generally look like this. I'll show you a slightly newer model there now. So that's a Mitsubishi today. We've used it. I've used that photo for 2 reasons, 2 mortal sins here as far as I'm concerned. When we take heat out of air in Ireland, in other words, you know, that condenser that you can see in here, you can see there's a slightly blue tinge to it. So that's that blue fin coating I was talking about. Okay, Brian, I'll take a look at that after and I'll come back to you. Okay, I see your question there. Yeah, okay. So if that's probably to do with air temperature, I'm guessing, Brian. I'm guessing if that's up at 12 or 13 degrees or 15 degrees, it'll be putting out 11 kilowatts. Other than that, they're all rated at 7. Anyway, I'm talking to only Brian now. Sorry, guys. So the air gets pulled in the back. It's passing over a cold surface. We all know what happens when air with moisture passes over a cold surface, like we see with a pint of Heineken or a pint of Guinness or whatever. You get moisture hitting the dew point and condensing. So you get condensation on the back of this. It's a normal part of operation and there's no problem with it. And it's factored into all of the efficiency calculations. But when that water condenses, by the way, that water is a good thing because it contains energy. I heard yesterday from somebody that there's too much moisture in the air in Ireland. We could all probably agree with that. But from a heat point of view, that moisture contains energy. And you know, I know our average person or a lay person won't understand maybe that, but it contains energy that we can use. So moisture in the air is not a problem from our point of view. In this case anyway, for ventilation and stuff that's different, but from a heat point of view, high humidity actually suits us. But the downside is that you get this condensation running off. This unit has a drip tray inside in the base of it, but for some reason, I don't know who installed it. I'm hoping it's not Ashgrove, but that water running off onto the ground like that, you can imagine if that day it's -5, well, now you have a block of ice here on the ground and we have a court case. So that drip tray has to be installed. Actually, as part of it, you couldn't have not installed it actually, but it must not have been piped to a drain, or maybe it's just leaking. The second thing that's wrong here is you can see that there's very little distance between the back of that unit and the wall. We need about 100 millimeters there because all of the air that's being pulled into the unit has to come in from the back. And of course, if we limit the space there, well, you limit the air and therefore you limit the heat. And you actually end up affecting your efficiency. So they're all little things, right? Again, you know, you can have a sequence of those small mistakes that double the running cost in your house, right? And you might never know it. And all you'd ever say then is when you meet your friends in the pub, that Mitsubishi heat pump is a disaster, okay? So they're the two things there. If we had a retrofit scenario, our heat pump would look like this. You take out your old cylinder. This would be, again, this is a retrofit scenario. Take out the old cylinder. The coil has to be big enough to talk to the heat pump. So this heat pump here on the left, the pipes would run up through this here. If this was a new house, of course, you wouldn't see those pipes at all, but we run it up in something that looks like a downpipe, a rainwater downpipe. That'll pop into the attic and across and down into your hot press, and you have another unit which talks to the outdoor unit here. And then the two pipes coming off to the bottom then, they'll either be doing hot water or heating. In winter, obviously, you'll be doing both. As somebody draws off the hot water, when it feels, when the brains sees that the water temperature has dropped to a critical point, it'll say, stop the heating for a few minutes and it'll go and do the hot water as a priority. And then it'll go back to heating. In summer, there's an outdoor temperature sensor on the back of this unit here. And once it sees that it's above 15 or 17 or 18 degrees or whatever we set it at, it says, right, it's summer here. The house is at temperature and it's not getting colder outside. I'm just going to switch off the heating. Right now, you can actively switch it off yourself because sometimes during the summer the temperature might drop a tiny bit, and you know the unit would then automatically come back on. Some people would say in July, if it drops a little bit in temperature, we don't care. We put on a hoodie. So, but you can do whatever you want. But again, goes back to the local plumber telling you, don't put your hand near that unit. You know, you'll die. Stay away from it, right? And we're hearing that for a long time, and it doesn't help the industry. We have a whole pile of people out there now, installers as well as homeowners, who are not educated on how to use this technology. So, so that's that. Let me go forward. So that's a more modern looking outdoor unit. And then the controls. So do I have to leave it on all the time? I think I've answered that. You do not have to leave it on all the time. In fact, if we were doing something like a church, which is, you know, we use the example of a church because obviously, you know, in most cases, it's only used on a Sunday. It's typically an inefficient building. So why would I leave it on after Mass on a Sunday, leave it on all the way through the week until next Sunday morning? You know, would I not just turn it off? The answer is yes. Because I've turned it off though, and I need to heat the church up quickly on the Sunday morning, the heat pump now needs to be bigger. The radiators need to be bigger, the pipes, the pumps, all the rest of it. So there's a bit of intelligence. If I operate it on an on-off basis, there are things that I have to be smart about. But we can do it. If you have a house that's kind of pushing away from the efficient houses we've looked at towards the church in terms of efficiency, there's a strong argument for turning it on and turning it off. You know, give it a few hours in the morning, a few hours in the evening. Let the house drop during the day. But keep in mind, you know, a heat pump typically isn't as big as an oil boiler, so it'll react a little bit slower in the evening. So you need to predict maybe a little bit closer, or a bit more, I suppose, carefully when you need to turn it back on. And of course, that problem will be magnified in really cold weather. So in mild weather, it won't matter because it'll react plenty quick enough. Is more thermostats better? Sometimes it is, sometimes it's disastrous. We often say that, you know, especially in a big house or a house maybe with, you know, let's call it a 3,000 square foot house or 270 square meters, you know, you can have 10 thermostats, and maybe you're a local electrician or maybe even your plumber would say, look, the thermostats are a good thing and we'll go for the highly efficient ones and they're very accurate. That can be a disaster. And the reason is, if you take, go back to our, we'll just take a 10 kilowatt heat pump as an example. 10 kilowatts is big enough for the house on the coldest day of the year. So by definition, for every other day now, it's too big. And especially if you have a house maybe 13 or 14 degrees outside, the house only needs a tiny bit of heat, if it needs anything. And every time a thermostat decides, I'm not at the 20 degrees I was asking for, it might only be 19.9, and no homeowner will realize the difference between 20 and 19.9. You simply won't know it. But the thermostat will know it, and it'll say, I want heat. What it's going to do now, keep in mind that that room might need 100 watts. Now, 100 watt is a bulb. It might even need less. But to get that 100 watts, it's going to start up a 10,000 watt machine out the back of my house. And, you know, because it's underfloor heating, it'll take a while to heat up the floor. The heat pump is going to be starting and stopping because it can't get rid of the heat quickly enough. And so it's like city driving in a car, you know. And when all of that is finished in an hour, my house is now, or my room is up to 20 degrees, it'll say, thank you very much, the thermostat switches off. And I can then have another room that decides, I want 0.1 of a degree. So a seemingly intelligent system can actually do really, really dumb things. It'll control the temperature very accurately, but there's a massive cost to efficiency, okay? And so we would say thermostats, unless you're going to go very intelligent with them, the middle step is quite dangerous. By the way, heat pumps by themselves are extremely intelligent. What they're doing is they're watching the outdoor temperature. So take a day like today where it's, I can't remember, 15 degrees or something outside. The heat pump is saying, I don't need heat, the house is hot. If the sun goes down and it gets cold, long before my indoor thermostats will say, I need heat, the outdoor thermostat sitting on the heat pump will say, it's dropping in temperature outside here. This house is going to need heat in a few hours. I'm going to start reacting now. Because if it reacts early enough, it can react nice and slowly at a low temperature, which is very efficient. If it waits for that thermostat to open, which is too late, it has to run at a high temperature to get the heat up quickly, and of course drags down your running cost. The other thing it does, of course, is it creates overheating, because I've been running now at a high temperature into rooms like my kitchen that needed 13 watts, and now I get overheating in those rooms, which is a problem actually I didn't discuss a while ago, but I'll go back to it in a second. Can I have a night rate meter? For a good few years, up until about 2 years ago, we told people, unless they had a very large house, not to get a night rate meter, but it's back to the stage again where night rate is probably a good thing, but it depends on the house, right? Keep in mind that if you get in a night rate meter for your heat pump, your night rate is typically half price, but your day rate goes up, okay? So you better be sure that whatever gain you have at night isn't being more than lost by day, okay? So yeah, you can. Some cases you should, in some cases you should not. Can I do hot water only in summer? We've answered that. Yes, is the answer, and it does that automatically. Do I need aluminium radiators if I don't have underfloor heating? No, you don't. This is a myth that's out there for about 20 years. Aluminium radiators tend to be lighter, and therefore there's a perception that they need much less heat to heat your room. It's not in fact true, but you know, the myth has stayed there. But they do tend to be smaller now, to be fair, but you don't have to have aluminium. So quite often in retrofit, we would still use steel. Unless we're really cut for space, we would go to aluminium, but there's a big jump in cost. I'm just going to go back there for 2 seconds and just make a point that I forgot to make. I'm just going to go back to the situation here where I was running my heat pump here, at 50 degrees because I was trying to reach my 109 watts in my conservatory. I'm now running at 50 degrees. I still can't heat my conservatory, but keep in mind the rest of the house only needed 13 watts, and I'm now running at 50. Look what I'm getting. I'm getting 200 watts into a room that wanted 13 watts, right? Or if I put the pipes in at 6 inches, it's 172 watts, or 200 millicenters. I'm getting 150 watts per square meter where I only wanted 13. I forgot to say it a while ago. And then I get this 33-degree floor temperature, which I heard about only in the last week in another very large house not too far from our office here. But not only has the wrong floor covering in the conservatory meant that I can't heat the conservatory, which we often hear, but because I'm trying to heat that conservatory, I've had to go to a very high temperature, doubling my running cost or maybe trebling my running cost. But I've also caused hot and cold spots all over the house. So the kitchen is now roasted because it has tile. The bathrooms will be roasting. And, you know, the tendency is just throttle down the flow into the floor, which even creates a bigger problem because now the hot water getting into my kitchen is now roasting, and I slow it down. By the time it gets to the far side, it's freezing. So I have hot and cold spots all over the house. And, you know, in a car showroom, maybe you get away with something like that, but in a house, it's simply, you know, you're paying for it. It's not efficient. It's not comfortable. The air is now too hot. You're starting to get the dry nose and all of that stuff. Anyway, I'll keep going. I forgot to make the point that the conservatory can cause overheating in every other room because we had to ramp the heat pump up to 100 miles an hour to try and heat the conservatory. So the question here, can you have a separate underfloor heating zone for the little used downstairs? So yeah, you will have zones. Every room will have its own zone. There's no question, David. And for a little used room, yeah, you can. There's no problem with that. Zoning it is no problem. The zoning that we will say of that conservatory that we just looked at, you know, the heat pump is sitting here in the plant room. It's producing water for the whole house. It has to pick the hottest temperature that's required. Yes, it'll be on its own zone. What we would do with that house is if we couldn't heat it and the customer was insisting on, I don't know, parquet floor or carpet, we would actually remove it from the rest of the system, and we would maybe we would connect it to the hot water cylinder, which is already at high temperature, but we wouldn't drag down the efficiency of the entire system. I don't know if I'm answering your question there, David. So yes, you can have zoning. Spare better not use. Yeah, you can have as much zoning as you want, David. I just want to make the point that it doesn't fix the problem out here, because once one room needs a high temperature, they're all getting the high temperature. Now you can actually start mixing it down for the other rooms, but it doesn't matter. Well, it stops the overheating, but you've already incurred the running costs. Okay, so we're moving along. 6. What time have we? Oh, sorry, I nearly used bad language. 2 seconds. So I'd say we're more or less finished, guys. What I would say to anyone there is make sure you switch energy supplier yearly, right? We're seeing electricity prices today between 40 and 25 cents for day rate and 14 and 15 cents by night rate. Be sure to change, because otherwise they leave you at the same rate or shove it up a bit. We see it every year. So use Bonkers or somebody like this, and all you need to do is just threaten to leave, and you're going to get reductions of up to 40%. We saw it there ourselves there recently. In some cases, you're getting free electricity from some of them at certain times of night, in which case you could force your heat pump to operate a little bit harder if you wanted to. So you could actually ramp the temperature up. Okay, despite everything I've just said, you can run your heat pump at 35 or 40 or 45 degrees. Yes, you're affecting your efficiency, but you're getting it for free. So, and then export rates is only for solar. So guys, our Ashgrove YouTube channel, there's a lot of explainer videos there. Some of them are for technicians and not really aimed at end users or designers. Some of them are for the users then, and some of them are just explainers and so on. But I suppose unless you're a designer, the next bit here, installation methods, especially in houses like the one we just looked at, there's different types of piping arrangements. What you typically is serpentine. The other two are more technical for houses with very different heat loads. So the conservatory that we just used, we would actually start using reverse spiral or reverse serpentine. It prevents that hot and cold spots that we often see where we have that conservatory or that room that needs a lot of heat. We're going to get hot and cold spots everywhere else if we do that, and therefore to equalize, we use these reverse spiral and serpentine. And anybody who wants that slide, shout and we can send it to you. So the conclusions, give me 2 seconds to just check the questions. David told me I should have asked so that those spare rooms set at a lower temperature than the rest of the house. Yes, David, yeah. So if you have rooms, the question is there, guys, if I have a room that I'm not really using, or that when the kids leave, can I turn that room down? The answer to that is 100% yes. It's like a radiator. You have a little throttling valve, or if you have a thermostat on it, you can just turn it down. We would prefer the former. Just throttle the flow down, and you can set the room at 13 degrees or 15 degrees or whatever you want, and you can turn it back up then when you want it. So certainly you can do that, David. That's no problem. And yeah, there's a chance actually we have videos explaining that on the YouTube channel, David, but contact us if there isn't. So conclusions: floor coverings and radiator size are the single most important thing that will dictate success with the heat pump. Nothing to do with the heat pump. We can use a bad heat pump or a good heat pump. If these two things are wrong, it doesn't matter what sort of a heat pump you have. You need to control it correctly. By the way, when I'm including there the floor coverings, I'm also including the pipe centers as part of that calculation. So control it correctly. Control the temperature sensibly. So we do see people there, they move into the house and they get used to the 23 degrees. Very hard to go back from it, okay? And as I say, every degree that you have it above 20 or 21, each one of them is costing you 4% extra. Change your electricity provider every year. And please use conscientious tradespeople, people who have an interest in, calculating things properly. I'm not saying come to Ashgrove, but whoever you're using, we want to see a bit of science. We hear all the time, I hear it, we throws in plenty pipe. That sort of an answer for me is an immediate red flag. This guy needs to be gone. And, we're here, I would say 70% of what we see is poorly done by a person who thinks he's doing the right thing. He learned something 10 years ago, he's held on to that, but there's no continuous learning. So yeah, everything, when we went back to houses in 2005, we were measuring every house that we did. We'd install your heat pump today, we would go back to it a year later to service it. Well, we expected it to use 35 kilowatt hours per square meter per year. What did it use? And we could tell from the meters, okay, it used slightly more, slightly less. Why? Did we get it wrong? In some cases, what we started to see was dormer houses were using much more energy than everything else. So we started to investigate dormer houses, and we could see that there were weaknesses. And we started to advise people certain things, maybe to consider if they were going building a dormer, and so on and so on. But we're measuring those now. We've thousands of houses where we've the data, but it's the only way. Put it in, let it run. Obviously we expect it to operate, but sometimes for some reason or another, it mightn't be where we thought it was. Well, why? Did we make a mistake? Do we have to go back and fix it? What can we learn going forward? Lastly, this is a disastrous one in Ireland. We don't service anything until it breaks down. We know that, and then we'll ring up Ashgrove or somebody like that. We'll roar and shout to get it done this evening. Unfortunately, most of that happens in, imagine turning off your car in April and going back to it in October to turn it on and wondering why it won't start. Sometimes there might be a dirty filter or dirty pump, a little bit of whatever it is. Ideally service them. They should go without saying. So we do seminars, guys, mainly for home upgrades. We do some solar ones. You'll see them there every second. That's actually the old calendar now, but we do, as I said, 200 of them a year. They're there, they're free, and we're happy for you to join them, and we won't be pestering you with emails. I have another question that might be of use. How often should ground source heat pump be serviced? You get away with less, Francis, than you would with an air source. I would say, look, the warranty says, for the period of the warranty, I would say every year, right? The reality after that is there's extremely little in them. The compressors are bulletproof. Every fridge, freezer, who services a freezer? You have pumps, but again, they're bulletproof. So I would say after the warranty, probably every 2 years would be fine, Francis. But with the air source, you have the fan. There's dust, potentially there might be leaves, because there's water running off the back of it. Any dust is going to maybe stick to the water, so that, in some cases, that would be worse than others. Other cases, you don't get any dirt building up on them. But yeah, so that's it. I think I've covered all the questions, guys. I hope this is of use to you. Feel free to ask anybody to join here. The intention is that it's there to help people make good decisions. It drives me mad when I hear poor stories, or I visited houses where I did last week, where they couldn't turn on the heating because the floors got too hot. That drives me nuts. And so we're trying to help as many people as we can. These webinars are simple enough for us to do, and hopefully they prevent other people making the same mistakes as what we see every day. Anyway, guys, thanks for all the nice comments there. Best of luck with your project. Okay, take care. Bye.